Hello, welcome to SPIE Medical Imaging 2021, the session of image registration. I'm Bolly, a postdoc researcher from Biomedical Imaging Group Rotterdam, Erasmus Medical Center. In this presentation, I will introduce a new method of deep learning-based unbiased group-wise registration, and the method of using joint segmentation for longitudinal image analysis. Since the method proposed here are generic to different image modalities, I hope this presentation can bring some ideas to your own research. Image registration is a procedure about determining a spatial transformation or a mapping that relates position in one image to corresponding position in other images. Conventionally, this transformation is determined for each specific set of input images using iterative optimization. Recently, using deep learning-based method, it is a nonlinear mapping function that is determined, so that for any given pair of input images, a most likely transformation between them can be easily inferred. As you are aware, deep learning-based registration methods have outperformed classical methods in terms of higher efficiency and comparable accuracy. This has been demonstrated by many of our familiar works, such as Voxomorph. However, due to an obvious limitation that it only supports pairwise registration using fixed reference image, algorithms based on deep learning cannot yet completely serve as an alternative to classical algorithms. In the setting of longitudinal image analysis, this means that we can either register a follow-up scan to the baseline scan or the other way around. In cases where multiple follow-up images of the same subject are available, a common strategy is to register all the images to the baseline space. This can actually introduce bias of interpolation towards the selected reference, since the reference baseline image remains original, whereas the rest images are smooth during image interpolation. In order to overcome these limitations and achieve unbiased longitudinal image analysis, deep learning-based methods have to first enable registration of multiple images and to register images to the mean space of the group. This is therefore the objective of the proposed method. Now let's get on to the method part. This figure shows the proposed Luger module of learning unbiased group-wide registration. From left to right, let's consider a group of input images I, each described by intensity values. The aim of our method is to simultaneously estimate a set of transformations T using a convolutional neural network, such that input images I can be warped to a common reference space and spatially correspond with each other. We have to remember that this common reference space does not exist in the real world. It is in the implicit space determined by the given input group. With this mean space strategy, we eliminate the need and the bias of selecting the reference image. Now let's move on to our next key point, loss function. To maximize spatial correspondence between registered images, a loss term LREG that measures structural or intensity similarity is often used, and combined with a penalty term LDEP for smooth deformation. In the present study, the imaging data is of single modality. Therefore, we use intensity-based similarity metric mean squared error to quantify the misalignment between registered images. Equation 1 is formulated following the approach of MATES, in which the average image of the registered group can be considered as an implicit reference image or a template image of the group. Subsequently, to encourage smooth deformation, we include a diffusion regularization term on the estimated velocity field, which has been widely used in literature. Now, with the similarity and smoothness terms, input images are being aligned in a certain implicit space. But there actually can be infinitely many spaces that fulfill equation 1. How can we make sure the estimated space is in the mean space of the group? Or in other words, how can we apply the constraint of geometric centrality? A straightforward solution is to include a loss term to minimize the average velocity field, similar to the strategy used in the literature for atlas construction. But this strategy, on the other hand, will introduce an additional hyperparameter to optimize, and the constraint of centrality may not always be satisfied. To get rid of the additional loss term, and to have the constraint being always satisfied, we propose a constraint optimization strategy to force the geometric centrality within the neural network. For this, inspired by classical algorithms, we subtract the average velocity field from each of the estimated velocity fields, resulting in their sum to be 0. This operation is implemented using a custom layer in neural network, which we denote it as constraint projection and marked it in yellow in the figure. In this way, the proposed Luger framework is optimized with regard to loss terms of intensity similarity and deformation smoothness only, but always subject to the constraint of geometric centrality. Now let's move on to our next contribution, an unbiased framework for longitudinal image analysis. As I have mentioned in the beginning, pairwise fixed reference registration can introduce a bias of image interpolation, and also a bias to subsequent statistical analysis if baseline image is consistently used to initialize the segmentation of follow-up images. Moreover, as most existing segmentation algorithms are designed for cross-sectional studies, a direct use of such method in longitudinal analysis can very likely lead to inconsistent segmentation across multiple time points. To eliminate this bias, we present a new framework for longitudinal image analysis, making use of the proposed Luger module. As it is shown in the figure, a segmentation network f theta is attached to the registered images in the mean space and outputs a segmentation of the implicit reference image. Subsequently, we warp the obtained segmentation back to image native space to minimize classification error with regard to the segmentation label. This framework has several advantages. First, information from all available time points can be jointly utilized for image segmentation, which results in less random error comparing with cross-sectional segmentations. Second, a common segmentation is obtained in the common space, ensuring spatial correspondence of the segmented structures across images, which means that the variation in segmentation can be fully explained by spatial deformation rather than classification error. Third, during a simultaneous optimization of the segmentation and registration, the way we formulate segmentation loss term, LSEG, in image native space can optimize the inverse transformations as well. We apply the proposed unbiased longitudinal framework to the analysis of white matter tract from diffusion-weighted MRI data. So, white matter tracts are functionally grouped axonal fibers. They are thought to subserve particular brain functions, for instance, memory, cognition, or execution. Quantitative analysis of white matter tract therefore plays an important role in bridging the interpretation of imaging biomarkers with brain functioning, and in the study of neurodevelopment and neurodegeneration. Yet, from the figure in the right side, we know that the segmentation of white matter tract is non-trivial. One of the main challenges in tract segmentation is that the tract cannot be directly identified from diffusion MRI, and there is no manually annotated ground truth in vivo. Also, white matter tract can have complex geometry where the image resolution for diffusion MRI, especially clinical quality diffusion MRI, is quite low, comparing with structural imaging. In the present study, for model training and evaluation, we generated segmentation labels of white matter tract using a widely applied classical method, which consists of probabilistic tractography and atlas information. The longitudinal diffusion MRI images used in this work are from Rotterdam study dataset. Data from a set of 97 normal individuals who were scanned twice within a month was used for evaluations of reproducibility of the method, in which no changes in brain microstructures are expected. The scans from remaining individuals were repeatedly acquired in a time interval of 1 to 5 years. These data were further split into training, validation, and test set based on the participants. We compare the proposed means-based longitudinal framework with an existing pairwise framework that uses fixed reference registration. For fair comparison, we adapted this method to use stationary velocity field-based registration. In contrast to the proposed mean method, the fixed method registers a moving image to a target space. It segments the moving image and propagates it to the target space. And the segmentation consistency is explicitly optimized using a loss term, L-cons, rather than being forced within the network. To investigate the variabilities of evaluation metrics that due to small processing error, two additional reference methods are compared by applying morphology operations to the binary segmentations predicted by the proposed mean method. With dilation method, we quantify the changes in evaluation measures that solely due to a dilation of one voxel. Likewise, with the translation method, the changes due to the translation of one voxel along the axis perpendicular to the axial plane are computed. This figure shows an example in analyzing 3 time points. We illustrate the geometric centrality of the implicit reference image by visualizing it and visualizing the estimated velocity field. In the second column, visual inspection of the warped images and their median image in the common space showed plausible average anatomy among the input images in the first column. The right column shows estimated velocity field, mapping from image native space to the common space. Ending 3 velocity field give a total deformation of 0 at each corresponding location. These results together confirm that the reference space was indeed at the center of the deformations. Now let's turn our attention to the segmentation performance. The yellow structure in the third column shows a segmented forceps minor tract in image native space and in the mean space. The segmentation looks appeared correct at all time points and visually outperformed the segmentation labels as shown in blue. This improvement can be attributed to the use of image information from all time points. These results together confirm that the proposed method is able to simultaneously align images to the mean space of the group, and thus can serve as an elegant alternative to classical method. Now we move on to quantitative results. Using the reproducibility dataset, we evaluated the processing bias of the method in producing semantic segmentation and imaging biomarkers when time points were passed in reverse order, which for the fixed method means that different moving and target image were used. We observe several findings from this table. First, the proposed mean-space longitudinal framework achieved significantly better spatial correspondence of segmentation than the fixed method as quantified by the kappa coefficient. The results had almost perfect agreement, and the remaining error was even smaller than the translation of one voxel, which can easily happen due to subtle numerical instabilities and interpolation. Second, the reliability of the proposed method is also corroborated by the subtle variation in the determined imaging biomarkers. The percent variation of tract-specific volume, fractional anisotropy, and mean diffusivity measures all had non-significant difference from zero, and were numerically smaller than that of the fixed method. Third, the segmentation accuracy of the proposed mean framework did not improve over the fixed method. This might seem disappointing, but it is actually reasonable after a bit of thinking. Since the mean framework aims at reducing random errors in cross-sectional segmentations, at each individual time point, its overlap with segmentation label can indeed decrease. At last, we compare the segmentation consistency across 3 time points as quantified by the overlap dice coefficient in the mean space determined by the proposed group-wise method. Compared to the perfectly consistent segmentation achieved by the proposed method, the consistency of the fixed method that optimized using a loss term was suboptimal. To conclude, we present a deep learning-based framework for unbiased group-wide registration. Although there exists classical method, the proposed framework still wants a state-of-the-art by the first time enabling learning-based registration of multiple images to the mean space of the input group. Also, this method has impact beyond the presented application, and the mean space learning strategy can spread to the field of deep learning-based registration and their relevant research. Secondly, we further present a longitudinal framework for reliable and consistent image analysis. This framework introduces a novel way for learning-based longitudinal imaging studies and enables a fast construction of unbiased within-subject template, allowing reliable and efficient analysis of imaging biomarkers. My presentation today ends with this slide. It's a pity that we are not able to discuss insightful ideas face-to-face. Yet I would still be happy to receive your questions and suggestions through email or Slack channel. And I look forward to meeting some of you on many occasions in the future.